All right. So where do we leave off here? Table lookup. Ooh wee. Let's continue. In this section, we will write the innards of a table lookup package to illustrate more aspects of structures. This code is typical of what might be found in the symbol table management routines of a macro processor or a compiler. For example, consider the pound define statement. When a line like pound define in 1 is encountered, the name in and the replacement text 1 are stored in a table. Later, when the name in appears in a statement like state is equal to in, it must be replaced by 1. There are two routines that manipulate the names in replacement text. Install records the name S and the replacement text T in a table. S and T are just character strings. Lookup searches for S in a table and returns a pointer to a place where it was found, or null if it wasn't there. The algorithm is a hash search. The incoming name is converted to a small non-negative integer. Which is then used to index into an array of pointers. An array element points to the beginning of the linked list of blocks describing names that have the hash values. So it's basically a hash table. So they called this a table lookup. Interesting. It is null. Oops, did I? Yeah, okay. It is null if no names of hash have hash to that value. A block in the list is a structure containing a pointer to the name, the replacement text, and the next block in that list. A null pointer marks the end of the list. Let's get struct end list, table entry, next, name, definition. The pointer array is just define hash size 101. And then we have a static struct end list. Hash table, hash size, pointer table. So the static in this context means that it's local to the file. It's not referenced in other C files. The hashing function, which is used by both lookup and install, adds each character value in the string to a scrambled combination of the previous ones, and returns the remainder modular the array size. This is not the best possible hash function, but it is short and effective. So we have form hash value for string. We have our hash on our char star, because it's back a unsigned integer. So we allocate the space for that on the stack, and then we return that at the end. Mod the hash size for each hash value. For initialize hash value to 0. And then each iteration we compare the character currently being pointed at by S, and we say if it's not null, then we continue the body. We take that character, we add the offset 31, and we multiply that by the hash value. And then we do that over and over and over again until we hit the null byte. And the pointer is being advanced every time by this plus plus. Unassigned arithmetic ensures that the hash value is non-negative. Sorry, unsigned arithmetic ensures that the hash value is non-negative. Which should be a problem. I guess if hash value exceeds the unsigned maximum integer, it'll just overflow. And then it'll get modded down anyways, so it doesn't matter if it overflows. I guess it could matter, because you might be modding by a number that is different than a power of 2. Could be like an odd number, like it is in this example 101. which doesn't evenly fit into a power of 2 boundary that your unsigned would fit into. Yeah, it's like a normal integer, just 4. So it could easily be exceeded by, was that 4 billion value? Each character is what? 200 or 128, I guess, potentially, for ASCII. Plus 31, so let's just say 256. So that means that we need 256. Let's see. That means you have 3 bytes. So it'd be 2 to the power of 24 characters. 2 to the power of 24 is that many characters, which is about 16 megs. So about 16 megs you risk overflowing. I mean, it's not gonna really mess up the hash as long as it doesn't change. It should be fine. What do I pick this constant 31? Oh, and it's also multiplying it. Never mind. I didn't see the multiplication. So it'll definitely overflow. The hashing process produces a starting index in the array hash table. If the string is to be found anywhere, it will be in the list of blocks beginning there. The search is performed by lookup. If lookup finds an entry already present, it returns a pointer to it. If not, it returns null. So the lookup function computes the hash, stores it NP, and then while NP is equal to null, sorry, not equal to null, it compares the name with the value provided as an argument, S. If it matches, we return NP. Otherwise, we advance to the next element that it points to. If we fall off the end, you don't have a result and return null. The for loop in lookup is a standard idiom for walking along a linked list. Install uses lookup to determine whether the name being installed is already present. If so, the new definition will supersede the old one. Otherwise, a new entry is created. Install returns null if for any reason there is no room for a new entry. Okay, so we got the hash function, we got lookup, and now we have install. So install takes in the string that we're going to install and defn, which is a replacement text. So the name and replacement text of the struct, the endless struct. We then, let's see. Call lookup on name. If that is equal to null, then we malloc up our pointer. Sorry, malloc up a what do you call it? An endless node. Get a pointer to it, cast a pointer, and then we say if the pointer is null, that means malloc failed, or we couldn't duplicate the name into the pointer, then we return null saying, hey, we weren't able to install this. Errors occurred with some malloc or something. And then we compute the hash to get the hash val. Then we get the element at that location. And we set that to our next. and then we set ourselves into the hash table as the base. So as you're inserting elements, the current elements are getting pushed down into the list. So you don't get added on to the end, you get added on to the beginning. We used to call these buckets. Get put in a bucket with the rest of the values. Else we're already there. We free the definition, huh? So that means that so if lookup is null, we do all the stuff to add it in. Else we're already there. We're already been installed. In which case we have to free the definition because we have a new definition. We don't want to, we don't want to link. Sorry, we don't want to leak the previous definition. So we free it up, and then we do a duplication, and then assign that in def n. If that nulls out, then we return null. I kind of would prefer to have the duplication and null check up front, and only free the previous, like hold on to the reference, the previous value, try to do the duplication. If it fails, assign the previous value into there, and then continue, return null. So now you have a consistent state. You return null, you weren't able to do the work, but at least the thing's in a consistent state. Because here you've already freed def n. Then you do this thing where you assign into def n null. So that means that you've deleted that node's definition. And then you return null here. You don't need to do that. It's causing damage doing that. All right, we got some extras here. Write a function undef that will remove a name and definition from the table maintained by lookup install. Not doing that. Implement a simple version of the define processor suitable for use with C programs. Define based on the routines of this section. You also find get character and unget character helpful. Don't care about that. Build a C preprocessor. No thanks. It's already built. C provides a facility called typedef for creating new data type names. For example, the declaration typedef into length makes the name length a synonym for int. The type length can be used in declarations, casts, etc. in exactly the same way that the type int can be. Similarly, the declaration typedef char star string makes string a synonym for char star, or a character pointer, which may then be used in declarations and casts. So we got our string p. Then we got a string array. We got an alloc int that returns a string. Yep. Notice the type being declared in a typedef appears in the position of a variable name, not right after the word typedef. Syntactically, typedef is like the storage class extern, static, etc., or auto. We have used capitalized names for typedefs to make them stand out. As a more complicated example, we could make typedefs for the tree nodes shown earlier in this chapter. Yeah, so we just call it a tree pointer. This creates two new type keywords called tree node, a structure, and tree pointer, a pointer to a structure. Then the routine talloc could become tree pointer talloc. I don't like that. I'd rather just have a pointer. Like just call it tree node and then star tree node. Or tree node star. It must be emphasized that a typedef declaration does not create a new type in any sense. It merely adds a new name for some existing type, nor are there any new semantics. Variables declared in this way have exactly the same properties as variables whose declarations are spelled out explicitly. In effect, typedef is like pound define, except that since it is interpreted by the compiler, it can cope with textual substitutions. Oops, sorry. I was on the wrong page here. So it can cope with textual substitutions that are beyond the capabilities of the preprocessor. For example, typedef int star pffi char star is char star. So you're saying, hey, typedef this function pointer, but you didn't give it a name. I guess pffi is the name. Oh, so it's just like a variable, like they're saying. Okay. Okay. So pffi becomes a function pointer for a function that takes two strings and returns an integer. Okay. Yeah, I mean, I like doing typedefs for function pointer types because they get annoying. Besides purely aesthetic issues, there are two main reasons for using typedefs. The first is to parameterize a program against portability problems. If typedefs are used for data types that may be machine dependent, only the typedefs need change when a program is moved. One common situation is to use typedef variable names for various integer quantities, then make the appropriate set of choices of short and long for each host machine. Types like size t and ptr diff t from the standard library are examples. The second purpose of typedefs is to provide better documentation for a program. A type called tree pointer may be easier to understand than one declared only as a pointer to a complicated structure. Unions. A union is a variable that may hold at different times objects of different types and sizes, with the compiler keeping track of size and alignment requirements. Unions provide a way to manipulate different kinds of data in a single area of storage without embedding any machine-dependent information in the program. They're analogous to variant records in Pascal. As an example, such as might be found in a compiler symbol table manager, suppose that a constant may be an int, a float, or a character pointer. So you have a constant. It may be an int, a float, or a character pointer. The value of a particular constant must be stored in a variable of proper type, yet it is most convenient for the table management if the value occupies the same amount of storage and is stored in the same place regardless of its type. This is the purpose of a union. A single variable that can legitimately hold any one of several types. The syntax is based on structures. So you got union utag, int, float, char star, u. So union utag u. Wonder if you have to give it a name. It's kind of like a typedef in that regard. The variable u will be large enough. Oh, so you are declaring a variable. Okay. The variable u will be large enough to hold the largest of the three types. The specific size is implementation dependent. Any one of these types may be assigned to u and then used in an expression, as long as the usage is consistent. The type referred must be the type most recently stored. It is the programmer's responsibility to keep track of which type is currently stored in the union. The results are implementation dependent if something is stored as one type and extracted as another. Syntactically, members of a union are accessed as union name.member or union pointer dash member. Ugh. Just as for structures, if the variable uType is used to keep track of the current type stored in U, then one might see the code such as uType is equal to int. Then we do the ival, float, fval, string, sval. You could also switch on it if those are numerical values. Switch on uType. Unions may occur within structures and arrays and vice versa. The notation for accessing a member of a union in a structure or vice versa is identical to that for nested structures. For example, in the structure array defined by so-and-so, the member ival is referred to as a symtable I u dot ival. Yeah. And the first character of the string sval by either. Yeah. Makes sense. In effect, a union is a structure in which all members have offset 0 from the base. The structure is big enough to hold the widest member, and the alignment is appropriate for all of the types in the union. The same operations are permitted on unions as on structures. Assignment to or copying as a unit, taking the address and accessing a member. A union may only be initialized with a value of the type of its first member. A union may only be initialized with a value of the type of its first member. Thus, the union U described above can only be initialized with an integer value. Interesting. So if we go back to that, yeah. So it has to be initialized with the integer value. Interesting. The storage allocator in chapter 8 shows how a union can be used to force a variable to be aligned on a particular kind of storage boundary. Alright, we're getting close to the end of this chapter. Bit fields. When storage space is at a premium, it may be necessary to pack several objects into single machine word. Some common use is a set of single bit flags in applications like compiler symbol tables. Externally imposed data formats such as interfaces or hardware devices also often require the ability to get a piece at pieces of a word. Imagine a fragment of a compiler that manipulates a symbol table. Each identifier in a program has certain information associated with it. For example, whether or not it is a keyword, whether or not it is external or static, and so on. The most compact way to encode such information is a set of 1-bit flags in a single char or int. Usual way this is done is to define a set of masks corresponding to the relevant bit positions, as in keyword, external, static. They all occupy different bits. Or you could do an enum, keyword, external, static. The numbers must be powers of 2, then accessing the bits becomes a matter of bit fiddling with the shifting, masking, and complementing operators that were described in chapter 2. Certain idioms appear frequently, such as flags, or equals external or static. Turn on the external and static bits in flags, while when we say external or static, negate that, and we'll set them to 0. And flags and external or static will set everything or is equal to 0. We'll see if any bits are set. Both bits are off. Yeah, okay. Although these idioms are rarely mastered, as an alternative, C offers the capability of defining and accessing fields within a word directly rather than by bitwise logical operators. A bit field, or field for short, is a set of adjacent bits within a single implementation-defined storage unit that we will call a word. The syntax of field definition and access is based on structures. For example, the simple table pound defines above could be replaced by the definition of 3 fields. Struct unsigned int is keyword. So this is a struct. Is it the colon syntax I'm not familiar with? Usually it's a semicolon, but now this is colon with 1. Maybe that means bits. How many bits? This defines a variable called flags that contains 3 1-bit fields. The number following the colon represents the fields within bits. The fields are declared unsigned int to ensure that they are unsigned quantities. Individual fields are referenced in the same way as other structure members. Individual fields are referenced in the same way as other structure members. Flags.is keyword, flags.is extern, etc. Fields behave like small integers and may participate in arithmetic expressions just like other integers. Thus, the previous examples may be written more naturally as fields is extern is equal to field is static is equal to 1 to turn the bits on, and that to turn them off. And then flags is extern. And because equals, you could just say not flags is extern and not flags is static. Or you can say not flags is extern or flags that is static to test them. Almost everything about fields is implementation dependent. Whether a field may overlap a word boundary is implementation defined. Fields need not be named. Unnamed fields, a colon with width only, are used for padding. The special width 0 may be used to force alignment at the next word boundary. Fields are assigned left to right on some machines and right to left on others. This means that although fields are useful for maintaining internally defined data structures, the question of which end comes first has to be carefully considered when picking apart externally defined data. Programs that depend on such things are not portable. Fields may be declared only as ints. For portability, specify signed or unsigned explicitly. They are not arrays. They do not have addresses, so the ampersand operator cannot be applied to them. Interesting. I've never seen the bit fields, but it's good to know they exist. Okay. Input and output. So let's see how many pages this is. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 18 pages on input and output. Let's look at some of the topics. So we got standard, input and output, which is read and write. Of course, they don't define those that way. They talk about shell stuff, formatted output, printf. We got variable length argument lists, variadic arguments, formatted input scanf. Might be nice to revisit scanf since I haven't used that in a while. File access. Not sure why I need to do that. I guess maybe just okay. Standard error and exit. Line input and output. Miscellaneous functions. Okay, I mean, this isn't too crazy. And there's some things in here that kind of interest me. So let's go ahead and dive in. Input and output facilities are not part of the C language itself, so we have not emphasized them in our presentation thus far. Nonetheless, programs interact with their environment in much more complicated ways than those we have shown before. In this chapter, we will describe the standard library, a set of functions that provide input and output, string handling, storage management, mathematical routines, and a variety of other services for C programs. We will concentrate on input and output. The ANSI standard defines these library functions precisely so that they can exist in compatible form on any system where C exists. Programs that confine their system interactions to facilities provided by the standard library can't be moved from one system to another without change. The properties of a library functions are specified in more than a dozen headers. We have already seen several of these, including standard IO, string.h, ctype.h. We will not present the entire library here since we are more interested in writing C programs that use it. The library is described in detail in Appendix B. Standard input-output, as we said in Chapter 1, the library implements a simple model for text input and output. A text stream consists of a sequence of lines. Each line ends with a new line character. If the system doesn't operate that way, the library does whatever is necessary to make it appear as if it does. For instance, the library might convert carriage returns and line feed to new line on input and back again on output. The simplest input mechanism is to read one character at a time from the standard input, normally the keyboard, with getChar. getChar returns the next input character each time it is called, or EOF when it encounters a file, and I guess it blocks forever. The symbolic constant EOF is defined in standard IO.h. The value is typically -1. But tests should be written in terms of EOF so as to be independent of the specific value. In many environments, a file may be substituted for the keyboard or by using the shell less than convention for input redirection. If a program prog uses getChar, then the command line prog less than infile causes prog to read characters from infile instead. Switching of the input is done in such a way that prog itself is oblivious to the change. In particular, the string infile is not included in the command line arguments in argv. Input switching is also invisible if the input comes from another program via pipe mechanism. On some systems, the command line other prog pipe into prog runs two programs, other prog, and pipes the standard output of the other prog into standard input for prog. The function int putChar int is used for output. PutChar puts the character C on the standard output, which is by default the screen. PutChar returns the character written, or EOF if an error occurs. Again, output can usually be directed to a file with greater than file name. If prog uses putChar, prog greater than out file will write the standard output to out file instead. If pipes are supported, prog pipe another prog puts the standard output of prog into the standard input of another prog. Output produced by printf also finds its way to standard output. Calls to putChar and printf may be interleaved. Output appears in the order in which the calls were made, depending on buffering, I guess. putChar might interact with the printf buffers. I'm not really a user of putChar, but I imagine it does. Each source file that refers to an input-output library function must contain the line include standard IO.h. Before the first reference, when the name is bracketed by less than and greater than, a search is made for the header in a standard set of places. For example, on Unix systems, typically directories user include. Many programs read only one input stream and write only one output stream. For such programs, input-output with getChar, putChar, and printf may be entirely adequate and is certain enough to get started. This is particularly true if redirection is used to connect the output of one program to the input of the next. For example, consider the program lower, which converts its input to lowercase. Wait a minute. Lower does not exist. Oh, this is a program that they implemented in the yeah. So you just get car, convert it to lower, put car. The function toLower is defined in ctype.h. It converts an uppercase letter to lowercase and returns other characters untouched. As we mentioned, either earlier functions like getChar and putChar in standard io.h and toLower in ctype.h are often macros, thus avoiding the overhead of function call per character. We will show how it's done in section 8.5. Regardless of how the ctype.h functions are implemented on a given machine, programs that use them are shielded from knowledge of the character set. Exercise 7.1. Write a program that converts uppercase to lower or lowercase to upper depending on the name it is invoked with. I don't care about that. Formatting output, printf. The output function printf translates internal values to characters. We've used printf informally in previous chapters. The description here covers the most typical use, but is not complete. For the full story, see Appendix B and printf char star format, arg1, arg2. Printf converts formats and prints its arguments on the standard output under control of the format. It returns the number of characters printed. The format string contains two types of objects: ordinary characters, which are copied from the output stream and copied to the output stream, and conversion specifications, each of which causes conversions to be printed. Conversions and printing of the next successive argument to printf. Each conversion specification begins with a percent and ends with a conversion character. Between the percent and the conversion character, there may be, in order, a minus sign, which specifies left adjustment of the converted argument, a number that specifies a minimum field width. The converted argument will be printed in a field at least as wide. If necessary, it will be padded on the left or right if left adjustment is called for. To make up the field width, a period, which specifies the field's width for the precision, a number, the precision that specifies the maximum number of characters to be printed from a string, or the number of digits after the decimal point of the floating point value, or the minimum number of digits for an integer. And h, if it is an integer, is to be printed as short, or L. If it is a long, conversion characters are shown in table 7.1. If a character after the percent is not a conversion specification, the behavior is undefined. So we got int decimal number di. I use percent d most of the time. O, octal number. Yeah, imagine x is hex. U is an unsigned decimal number. C is a character. S is a string. F is a floating point number. E is a double. G is another double. Okay, and then P is a pointer, and percent is no argument. Is converted to print a percent. A width or precision may be specified as star, in which case the value is computed by converting the next argument, which must be an integer. Okay. For example, to print at most the max characters from a string, you do it that way. Okay, I didn't know about that. I'm going to highlight that because I learned something. Try to highlight stuff that I learned. Okay. Most of the format conversions have been illustrated in earlier chapters. One exception is precision as it relates to strings. The following table shows the effect of a variety of specifications in printing. Hello world, 12 characters. We have put colons around each field so that you can see its extent. Yeah. Okay. The warning printf uses a warning. Printf uses its first argument to decide how many arguments follow and what their types are. It will get confused if you get wrong answer, and will get wrong answers if there are not enough arguments or if they are the wrong type. You should also be aware of the differences between these two calls. Printf s fails if s contains %. Printf %s is safe. Function sprintf does the same conversions as printf does, but stores output in a string. So sprintf, you give it a pointer to a buffer, a pointer to the format, and then all your arguments. Sprintf formats the arguments in arg1 or 2. Can you give it a length? Probably sn printf. Probably. Man sprintf. Yeah, sn printf. Okay. Write a program that will print arbitrary input in a sensible way. As minimum, it should print non-graphic characters in octal or hexadecimal according to local custom, and break long text lines. I don't care about that. Variable length argument lists. So variadic arguments is interesting. We got some scanf stuff, file access, error handling, line input output, miscellaneous functions. Okay. Making progress. We're at what, 155? And before the appendices, it's 190 basically. Move my little camera here. All right. So we got about, what, 45? Let's see. 45 would be 200, so about 35 pages left of the book, of its primary text. So not a lot. And these exercises are not really interesting to me, so I'm not really going to do any of them. All right, 6 now. Let's do maybe about another hour. Try to get through this chapter and into the next. And then we'll just have a little tail end to do tomorrow. Okay. Variable length argument lists. This section contains an interpolation of a minimal version of printf to show how to write functions that process a variable length argument list in a portable way. Since we are mainly interested in argument processing, min_printf will process the format string and arguments, but will call the real printf to do the format conversions. The proper declaration of printf is int printf char format ... where the declaration ... means the number and types of these arguments may vary. The declaration ... can only appear at the end of the argument list. Our min_printf is declared as so-and-so. Since we will not return the character count that printf does. Okay, so we just return void. The tricky bit is how min printf walks along the argument list when the list doesn't even have a name. The standard header standard arg contains a set of macro definitions that define how to step through an argument list. The implementation of this header will vary from machine to machine, but the interface it presents is uniform. The type VA list is used to declare a variable that will refer to each argument in turn. In min printf, this variable is called AP for argument pointer. The macro VA start initializes AP to point to the first unnamed argument. It must be called once before AP is used. There must be at least one named argument. The final named argument is used by VA start to get started. Okay, so we got an example on this next page. Each call of VA arg returns one argument and steps AP to the next VA arg. Uses a type name to determine what type to return and how big a step to take. Finally, VA end does whatever cleanup is necessary. It must be called before the function returns. These properties form the basis of our simplified printf. Okay, so we declare this VA list AP, points to each unnamed argument in turn. And then we have our char star P and a char star sval, and then we have an int ival and a dval. So sval, ival, and dval are just probably like temporary placeholders for storing values, and the star P is probably I don't know what that is. We'll see. For the format. All right, so we say, hey, VA start, make AP point to the first unnamed arg. So we give it format just so it knows, hey, you're coming after the char star. So it points immediately after the char star. And then we say for format is equal to P initially. Wait a minute. Okay, so we're handling the format string here. So we say, hey, format. The first character format, we're going to point to the same location as the format. And then while the dereference of P is not equal to null, while there's a value other than 0, for the dereference of Z, we're going to advance our pointer. And we say if P is not equal to the percent sign, then we just put char P and continue. Otherwise, it is a percent sign, in which case we dereference, we advance P and we dereference the value that comes after the percent sign. And then we switch on that. So we have D, F, and S. And then the default is just to put the char. But in between here, we have the calls to VA arg AP integer. So you grab the next argument as an integer, and then we pass it into printf. And then we do the same thing for double. And then for string, we have to do it for a char star, where we say VA arg is AP char star. And that gives us back our char star. And basically, while it doesn't point to null, point to a 0 byte, I should say, we just put it out. And then when we're done iterating through all of the characters of the format string, then we call VA end. And there's no checking here to make sure that our argument list is the same as the formats. It's like, yeah, lots of holes in this one. But it's meant to just serve an example, so makes sense. Revise min printf to handle more than the other facilities of printf. No thanks. format input scanf. Okay, so this is the inverse of printf. Function scanf is, got a spammer. The function scanf is the input analog of printf, providing many of the same conversion facilities in the opposite direction. Scanf reads characters from the standard input, interprets them according to the specification format, and stores the results through the remaining arguments. The format argument is described below. The other arguments, each of which must be a pointer, indicate where the corresponding converted input should be stored. As with printf, this section is a summary of the most useful features, not an exhaustive list. Scanf stops when it exhausts its format string or when some input fails to match the control specification. It returns as its value the number of successfully matched and assigned input items. This can be used to decide how many items were found. On end of file, EOF is returned. Note that this is different from 0, which means that the next input character does not match the first specification in the formatted string. What's funny is like when you're doing IO, 0 is EOF. But here it is not EOF. EOF is in the negative value. Next call to scanf resumes searching immediately after the last character already converted. There's also a function scanf that reads from a string instead of the standard input. It scans the string according to the format and stores the results and values through arg1, arg2, etc. These arguments must be pointers. The format string usually contains conversion specifications, which are used to control conversion of input. The format string may contain blanks or tabs, which are ignored, ordinary characters not %, which are expected to match the next whitespace character of the input stream, conversion specifications consisting of the character %, an optional assignment suppression character, an optional number specifying a maximum field width, an optional HLL indicating the width of the target, and a conversion character. Conversion specifier directs the conversion of the next input field. Normally, the result is placed in a variable pointed to by the corresponding argument. If our assignment suppression is indicated by the star character, however, the input field is skipped. No assignment is made. An input field is defined as a string of non-white space characters. It extends either to the next white space character or until the field width, if specified, is exhausted. This implies that scanf will read across line boundaries to find its input. Since new lines are white space characters are blank, tab, new line character turn, vertical tab, in form feet. Conversion character indicates the interpretation of the input field. The corresponding argument must be a pointer as required by the call by value. Boop. Semantics of C. Conversion characters are shown in table 7.2. Okay, pretty much the same stuff, right? Decimal or integer. Octal, unsigned, hexadecimal characters. Character string not quoted. EFG, floating point values, percent literal, percent. Oh, Was I supposed to echo this? Yeah. Regardless, doesn't exist. Let me see. TR awk said Python can do it. There's plenty of things. Okay. Not really learning anything here. It has been about an hour. I told myself that if I got to a point where I didn't want to read anymore and I wasn't learning much, that I would take a quick break to mentally reset and then restart. Let's get this scanf stuff. The next part is file access. This is all going to be a review because I read the Linux programming interface. Error handling, standard error and exit, line input and output, miscellaneous functions. The Unix system interface. It might be nice to read some of this, even though I just got done reading the Linux programming interface. Touches on read and write, which is nice. The syscall stuff. I didn't even know there was a syscalls.h. Because I was using the sys/ stuff. Open, create, close, unlink. These are all things I'm very familiar with. So probably not gonna learn much. lseek, example and implementation of fopen and getc. I really don't need any of this stuff. Example listing directories. Really don't need any of this stuff. Statting files. fstats. Example is the storage allocator. Okay. Then it might be fun to do. I think that's the last part of the book here, is the storage allocator. So I think maybe the capstone project for this book is to start on a storage allocator, because that was one thing I wanted to get around to implementing, was a bump allocator. And just implementing your basic allocator would be a nice exercise here. And then we got reference manual, which is 9 plus 38, so that would be 47 pages. 49, no, 48 because it's an extra page here. Some of this is just grammar though. I mean, I'm not gonna read all the grammar. Yeah, I'm good on the grammar. It's kind of crazy how small the grammar is though. Would have thought it would be larger. And then we got standard library. Input outputs. This is just documentation for the standard library. Formatted outputs. We already kind of discussed all this. Scanf, printf. Says more shit in it. String.h, mathematical functions, utility functions, A2I, A2F, stir to D. Non-local jump, set jump, long jump. Signals, very brief section on signals. Date and time functions. Implementation defined limits. All standard stuff that we've covered already in gory detail in the Linux program interface. Summary changes, don't care about that. So I think appendices C and B I'm going to skip. I think appendice A I might review, but I'm going to delete the appendices out of the README because I don't think there'll be much utility in reading them. So we are done with that. We are on input and output. I feel like both of these are like pretty heavily already covered in the Linux program interface. I mean, so far this has been a pretty short book. It's not a lot here, which is good because I don't want to go on and on in detail about stuff. It is kind of like a tutorial, like Kerningham was saying. It's kind of like a tutorial. And most of this stuff I'm super familiar with, so I don't know why I needed to get through this, but I think psychologically I just wanted to finish this book. I started it in college, never finished it. I'm doing more C work, so it'd be nice to just have this kind of behind me. And it already took a couple days, so it's not like it's a huge waste of time. All right, let's finish this section on scanf, and then I'm going to take a break here. Come back to it. Conversion characters D, I, O, U, and X may be preceded by H to indicate that a pointer to a short rather than int appears in an argument list, or by L, letter L, to indicate the pointer to long appears in the argument list. Similarly, the conversion characters E, F, and G may be preceded by L to indicate that the pointer is pointed to double rather than a float in the argument list. As a first example, the rudimentary calculator in Chapter 4 can be written with scanf to do the input conversion. So we scan F into V, which are double. And then we output a tab character, the value, and then a new line. Value is V added to the sum. So it's a accumulator. I wouldn't call it a calculator. It's more of a accumulator. Suppose you want to read input lines that contain dates of the form 25th of December 1988. The scanf statement is %D, %S, %D. No ampersand is used with month name because it's already a pointer. Literal characters can appear in the scanf format string. They must match the same characters in the input. So we would read dates of the form month, day, year with the scanf statement. So. Scanf ignores blank line. So it ignores blanks and tabs in its format string. Furthermore, it skips over white space, blanks and tabs, new lines, etc. as it looks for input values. To read input whose format is not fixed, it is often best to read a line at a time, then pick it apart with scanf. For example, suppose we want to read lines that might contain a date in either the above forms above, so it's with slashes or with the spaces, and with a month as a string or otherwise as a number. So we do get line, and then we do scanf for the first version. And we say, hey, if you got 3 matches, then we're good. We'll print you out. Otherwise, we're going to try the next one. If we got 3 matches, you're good to print out. Otherwise, we just say, hey, you're invalid. So calls to scanf can be mixed with calls to other input functions. The next call to any input function will begin by reading the first character not read by scanf. Final warning, the arguments to scanf and scanf must be pointers. By far the most common error is writing that instead of the pointer to n, and n is some value in memory which gets interpreted as a pointer. This error is not generally detected at compile time, but I'm sure the linters freak the fuck out. Alright, write a private version of scanf analogous to bin printf from the previous section. Not going to do that. Write a postfix calculator of chapter 4 to use scanf and or scanf to do the input and number conversion. Not going to do that. Next, file access. Alright, so we got 1, 2, 3 pages in file access. And then we got error handling, which is 1.5. Line and input and output, which is like not even half a page because most of it's code. And then we're in miscellaneous function territory. Okay, I'm just going to blast through this stuff. I don't really feel like stopping here. Before I was kind of getting a little bit discouraged. I'm slowing down. All right. File access. The examples so far have all read the standard input and written the standard output, which are automatically defined for a program by the local operating system. The next step is to write a program that accesses a file that is not already connected to the program. One program that illustrates the need for such operation is cat, which concatenates a set of file names, named files, onto the standard output. Cat is used for printing files on the screen and as a general purpose input collector for programs that do not have the capacity of accessing files by name. For example, the command cat xc yc prints the contents of xc and yc and nothing else on the standard output. The question is how to arrange for the named files to be read, that is, how to connect the external names that the user thinks of to the statements that read the data. I don't understand what you're saying. The rules are simple. Before it can be read or written, this is just permissions for the operating system. A file has to be opened by a library function fopen. Fopen takes the external name like xxc or x or y.c, does some housekeeping and negotiating with the operating system, details of which needn't concern us, and returns a pointer to be used in subsequent reads or writes of the file. So that's using fopen. I use open because I don't like this standard library file IO stuff. This pointer, called the file pointer, points to a structure that contains information about the file, such as the location of a buffer, the current character position in the buffer, whether the file is being read or written, and whether errors or end of file have occurred. Users don't need to know the details because the definitions obtained by standard IO.h include a structure declaration called file. The only declaration needed for a file pointer is exemplified by file pointer fp, file pointer open fopen, char name, char star name, char star mode. This is mode a char star, really? That's weird. This says that fp is a pointer to a file, and fopen returns a pointer to a file. Notice that file is a type name like int, not a structure tag. It is defined with a type def. Details of how fopen can be implemented on the Unix system are given in section 8.5. The call to fopen in a program is fopen name mode fp. The first argument of fopen is a character string containing the name of the file. Second argument is mode, also character string, which indicates how one intends. Oh, it's because they use the little read write things. Yeah. It tends to use the file. They don't use the o create, o read write. They don't use those flags. Allowable modes include read, write, and append. Some systems distinguish between text and binary files. For the latter, a B must be appended to the mode string. Oh, I'm so far off. I'm so sorry. I've just been reading on my own here, not advancing. My bad. All right. If a file that does not exist is open for writing or appending, it is If a file that does not exist, it is open for writing or appending. It is created if possible. Opening a file, an existing file, for writing causes the old contents to be discarded, while opening for appending preserves them. Trying to read a file that does not exist is an error. And there may be other causes of error as well, like trying to read a file when you don't have permissions. If there are any errors, fopen will return null. The error can be identified more precisely. See the discussion on error handling functions at the end of section 1 in Appendix B. The next thing needed is a way to read or write the file once it is open. There's several possibilities, of which getC and putC are the simplest. getC returns the next character from the file. It needs a file pointer to tell it which file. getC returns the next character from the string referred to by fp. It returns EOF for error, end of file error. PutC is an output function. PutC writes a character C to the fp and returns a character written or EOF if error occurs, like getChar and putChar. getC and putC may be macros instead of functions. When a C program is started, the operating system environment is responsible for opening 3 files and providing file pointers to them. These files are the standard input, standard output, and the standard error. The corresponding file pointers are called standard in, standard out, standard error, and are declared in standard io.h. These are file pointers, not file descriptors. Normally, standard in is connected to the keyboard, and standard out and standard error connected to the screen. But standard in and standard out may be redirected to files or pipes, as described in section 7.1. getChar and putChar can be defined in terms of getC, putC, standard in, and standard out as follows. Or formatted input or output of files. The function fscanf and fprintf may be used. These are identical to scanf and printf, except that the first argument is a file pointer that specifies the file to be read or written. Format string is the second argument. Boop. fscanf, fprintf. With these preliminaries out of the way, we are now in the position to write the program cat to concatenate files. The design is one that has been found convenient for many programs. If there are command line arguments, they are interpreted as file names and processed in order. If there's no arguments, the standard input is processed. I think you can do both though, right? Like, what if I do like echo foo to foo, cat readme foo, but then I also do echo bar into that. Okay, so it ignores the standard input when you have arguments. What if I say that? Really? Is there a, if I do man cat, can I do read me like that? Yeah, look at that. Foo. There we go. So you can access standard in just with putting the dash there. But man cat. Number. I've never used that before. Never have used that before. There's so many things in Unix. Cool. I didn't know cat had so much functionality. Never had the need for it. Okay. Next page. Boop. So this is our cat program. So we got this file copy function, which we don't have forward declaration for, which is means it's not going to compile, but we'll go ahead and continue reading. So we allocate a file pointer. Oh, here's our forward declaration for file copy right there. So it's probably right hand is the source. No, left hand is source. Right hand is the destination, which is the opposite of all the other conventions, which are right to left. Argc is equal to 1. Then no args, and we're going to copy from standard input to standard output. While argc, wait a minute, what? Oh, okay. While argc is being decremented, so we decrement it once initially, and while it's greater than 0, we're going to also do an fopen on argv decremented, dereferenced, saying, hey, read only. If that gives you a null, then we just exit. Otherwise, we get that fp out, which is a file pointer, not a file descriptor. And we file copy from the fp to the standard out, and then we close the fp. File copy just says, well, we get C on the input file pointer, and it's not equal to EOF, we put C to the output file. File pointer, standard in, standard out are objects of type file star. They are constants, however, not variables. So it's not possible to assign to them. The function fclose file fp is the inverse of fopen. It breaks the connection between the file pointer and the external name that was established by fopen. Freeing the file pointer for another file. Since most operating systems have some limit on the number of files that a program may have open simultaneously, it's a good idea to free the file pointers when they are no longer needed. As we did in cat, there is also another reason for fclose on an output file. It flushes the buffer in which putc is collecting output. Fclose is called automatic for each open file when a program terminates normally. You can close standard in or standard out if they are not needed. They can also be reassigned by the library function reopen. Reopen. Okay. Boop. Error handling, standard error and exits. Treatment of errors in cat is not ideal. The trouble is that one of the files can't be accessed, for some reason, the diagnostic is printed out at the end of the concatenated output. That might be acceptable if the output is going to the screen, but not if it's going to a file or another program via pipeline. To handle the situation better, the second output stream, called standard error, is assigned to a program in the same way that standard in and standard out are. Output written to standard error normally appears on the screen even if the standard output is redirected. Let us revise cat to write its error message on standard error. Program signals errors two ways. First, the diagnostic output produced by printf goes to standard error, so it finds its way to screen instead of disappearing down a pipeline or into an output file. We included the program name from argv0 in the message, so if the program is used with others, the source of error is identified. Second, the program uses the standard library function exit, which terminates the program execution when called. The argument of exit is available to whatever process called this one, so the success or failure of the program can be tested by another program that uses this one as a subprocess. Conventionally, the return value of 0 signals that all is well. Non-zero values usually signal abnormal situations. Exit calls fclose for each open output file to flush out any buffered output with main return expression is equivalent to exit expression. Exit has the advantage that it can be called from other functions and that calls to it can be found with a pattern searching program like those in chapter 5. The function is also underscore exit. The function ferror returns non-zero if an error occurred on the stream fp. Other output errors are rare. They do occur, for example, if a disk fills up. So production programs should check this as well. The function feof file is analogous to ferror. It returns non-zero if end of file has occurred on this specific file. We have generally not worried about exit status in our small illustrated programs, but ND series programs should take care to return sensible, useful status values. Line input and outputs. Standard line provides input routine fgets and a similar getLine function that we have used in earlier chapters. Fgets, charstar, maxLine, fp. Fgets reads next input line, including a new line from the file fp into the character array line. At most, maxLine -1 characters will be read. The resulting line is terminated with a null byte. Normally, fgets returns line on end of file. On error, it returns null. Our getLine returns the line length, which is more useful. Value 0 means end of file. For our output, function fputs writes a string, which need not contain new line to a file. If it so-and-so fputs, it returns EOF if an error occurs and 0 otherwise. The library function gets and puts are similar to fgets and fputs, but operate on standard and standard out. Confusingly, gets deletes the terminal new line and puts adds it. That's not confusing. To show that there is nothing special about functions like fgets and fputs, here they are, copied from the standard library on our system. I really don't need to look at those. The standard specifies that ferror returns non-zero for error, fputs returns EOF for error, blah, blah, blah. Write a program that compares two files, printing the first line where they differ. Nope. Modify the pattern finding program of chapter 5 to take its input set from a set of named files, or if no files are named as arguments, from the standard input. Should the file name be printed when a matching line is found? Don't care. Write a program to print a set of files starting each new one on a new page with a title and running page count for each file. Okay. Miscellaneous functions. There we go. Now we're getting towards the end here. Okay. Standard library provides a wide variety of functions. This set is brief synopsis of the most useful. More details, many other functions can be found in Appendix B. String operations. We've already mentioned the string functions stir len, stir copy, stir cat, and stir compare found in string.h. And the following S and T are char stars, and C and N are ints. So we got stir cat, stir end cat, stir compare, stir end compare, stir copy, stir end copy, stir len, stir char. Return a pointer to first C and S or null if not present. Stir archer. The last C and S. Okay. Character class testing and conversion. Several functions from ctype.h perform character tests and conversions, and the following. C is an int that can be represented as an unsigned char or EOF. Function return the functions return int. Is alpha non-zero if C is alphabetic, 0 if not. Is upper, is lower, is digit, is aldum, is space, is upper, 2 upper, 2 lower. On getC, standard library provides a rather restricted version of the function ongetch that we wrote in chapter 4. It's called ongetC, pushes the character C back into FP, and returns either C or EOF. For an error, only one character of pushback is guaranteed per file. ongetC may be used with any of the input functions like scanf, getC, or getchar. Command execution. The function system char star executes command contained in the character string S. I hate system because it uses a shell and it does too much work. Then it resumes. I'd rather just do a clone or fork myself, like fork and exec myself, than deal with all the complexity of this thing. Let's see. So it executes the command contained in the character string S, then resumes execution of the current program. The contents of S depend strongly on the local operating system. As a trivial example, on Unix systems, the statement system date causes the program date to be run. It prints the date and time of the day. It's the standard output. System returns a system-dependent integer status from the command executed. In the Unix system, the system return is the value returned by exit. Storage management. The functions. Sorry, I'm on the wrong page here. There we go. Storage management. The functions malloc and calloc obtain blocks of memory dynamically. Malloc, give it n, gives it back void star of uninitialized memory. Returns a pointer n bytes of uninitialized storage or null if a request cannot be satisfied. Calloc basically is an array allocation. You say here's this the number of elements I want to allocate and the size of those elements, and it gives you back a pointer to that memory that is 0 initialized. Returns a pointer to enough space for an array of n objects of the specified size, or null if the request cannot be satisfied. Storage is initialized to 0. Pointer returned by malloc or calloc has proper alignment for the object in question, but it must be cast into an appropriate type, as in int IP. So, or int IP. Yep. Makes sense. Free P frees the space pointed to by P where P was originally obtained by a call to malloc or calloc. There are no restrictions on the order in which space is freed, but it is ghastly error to free something. There's no restriction on the order in which space is freed, but it is ghastly error to free something not obtained by calling calloc or malloc. It is also an error to use something after has been freed. Typical but incorrect piece of code is this loop that frees items from a list. So for P is equal to the head initially, while P is not equal to null, we get next. And we call free P. The problem is that P next is already gone by the time you dereference it. So it could be being used by something else. Probably is not going to cause a crash, but it is wrong. The right way is to save whatever is needed before freeing. Exactly. Section 8.7 shows implementation of storage allocator like malloc. That's what I'm looking for. In which allocated blocks blocks may be freed in any order. Mathematical functions. There are more than 20 mathematical functions declared in math.h. Here are some of the more frequently used. Each takes one or two double arguments and returns a double. So you get sine, cos, arctangent 2, exponential, log base 10, power, square root, absolute value, but with an f. Not sure what the f is. Random number generator. The function ran computes a sequence of pseudo-random integers in the range 0 to rand max, which is defined in standard lib.h. One way to produce random floating point numbers greater than or equal to, one way to produce random floating point numbers greater than or equal to 0, but less than 1, is to define frand, to call rand, converting it to double, divided by the rand max plus 1. If your library already provides a function for floating point random numbers, it is likely to have better statistical properties than this one, I'm sure. Function srand unsigned sets the seed for rand. Portable implementation of rand and srand suggested by the standard appears in section 2.7. Functions like is super can be implemented to save space or to save time. Explore both possibilities. Sorry, is upper. Is upper. Let's see. Let's go back and see what that was. There's 2 upper. Is upper takes C. Non-zero if C is uppercase, 0 if not. Well, you can just check to see if C is in a specific range. C is just an integer value. You can say, okay, are you in the range of, are you greater than the uppercase A, greater than or equal to, and then less than or equal to uppercase Z. That doesn't take any space. I guess it takes a little bit of time to compute that. You could also do bit checks, because if we print out all the Python, if we get all the characters A to Z, so how do I do that? Ord of A, 65 to ord of Z, 90, for X in range 65 to 91. We're going to say print, and I'll give it a format string. I think this is how you do it now in Python. And we're going to give it the value X, and the value, which is like, I think I do it like this, sorry. X and bin of X. There we go. 1, 2, 3, 4, 5, 6, 7. So the 8th bit has to be 0, and the 7th bit has to be 1. But then there's a bunch of stuff that has the 7th bit 1 and 8th bit 0 that isn't in the range. I'm trying to think if you could do this with like a simple bit check, like a mask. Well, the 6-bit is 0 as well. So at least how many bits? 1, 2, 3, 4, 5. It can't be 0 here. It's a complex. Let's do another thing here where we do goes to sure of x. Oops. Zero, I think, is space, maybe? What's 64? What is 64? Oops. At sign, okay. Yeah, I think the range check is probably the best. I don't even know why I'm talking about this because I don't care about this exercise. All right. Clearly, it got me interested enough to experiment there for a second. All right. We are on the final chapter, the Unix system interface, which we read an entire 1,400-page book on. So I doubt we're going to learn much about the Unix system interface we don't already know. But maybe it'll be nice to get some perspective of how someone in the 70s and the 80s might have approached some of the Unixy stuff. And it has the allocator at the end, which is something that I want to play around with. All right, 6:45. I don't really feel like stopping. Been going for an hour and a half. Yeah, why don't we just keep on going here? All right. How many pages do you got? 69 up to... Oh, is it? A lot of stuff here that's not interesting. 69 up to 79 up to 89. So it's 20 pages. I think we didn't finish that. It would be nice to like get into the allocator, or at least do the allocator stuff tomorrow morning, so that's fresh in my mind. So we go into implementation. I don't know, I'm trying to feel out how I feel about this. I am supposed to like call it end of day by 6, but that's not happening today. All right, let's finish this. The Unix system interface. The Unix system operating system provides its services through a set of system calls, which are in effect functions within the operating system that may be called by user programs. This chapter describes how to use some of the most important system calls from C programs. If you use Unix, this should be directly helpful. For it is sometimes necessary to employ system calls for maximum efficiency or to access some facility that is not in a library. Even if you use C on a different operating system, however, you should be able to glean insights into C programming from studying these examples. Although details vary, similar code will be found on any system since the ANSI C library is in many cases modeled on Unix facilities. This code may help your understanding of the library as well. The chapter is divided into three major parts: input-output, file system, and storage allocation. The first two parts assume the modest familiarity with the external characteristics of Unix systems. Chapter 7 was concerned with an input-output interface that is uniform across operating systems. On any particular system, that the routines of the standard library have to be written in terms of the facilities that provided. All right, on any particular system, the routines of the standard library have to be written in terms of the facilities provided by the host system. In the next few sections, we will describe the Unix system calls for input and output and show how parts of the standard library can be implemented with them. File descriptors. In the Unix operating system, all input and output is done by reading and writing files because all peripheral devices, even keyboards and screens, are files in the file system. This means that a single homogeneous interface handles all communication between a program and peripheral devices. In the most general case, before you read or write a file, you must inform the system that you intend to do so, a process called opening the file. If you are going to write on a file, it may also be necessary to create it or to discard its previous contents. The system checks your rights to do so. Does the file exist? Do you have permission to access it? And if all is well, return to the program a small non-negative integer called a file descriptor. Whenever input-output is to be done on the file descriptor is used instead of a name to identify the file. File descriptor is analogous to a file pointer used in standard library or to the file handle of MS-DOS. All information about an open file is maintained by the system. The user program refers to the file only by the file descriptor. Since input and output involving keyboard and screen is so common, special arrangements exist to make this convenient. When the command interpreter of the shell runs a program, three files are open with the file descriptors 0, 1, and 2 called the standard input, standard output, and standard error. If a program reads 0 and writes 1 and 2, it can do input and output without worrying about opening files. The user of a program can redirect I/O to and from files with the less than and greater than sign. In this case, the shell changes the default assignments for file descriptors 0 and 1 to the named files. Normally, file descriptor 2 remains attached to the screen, so the messages can go there. Similar observations hold for input and output associated with a pipe. In all cases, the file assignment are changed by the shell, not by the program. The program does not know where the input comes from nor where the output goes, so as long as it uses file 0 or input for input and 1 and 2 for output. Low-level I/O read and write. Input and output uses the read and write system calls, which are accessed from C programs through two functions called read and write. For both, the first argument is a file descriptor, the second argument is a character array in your program where the data is to go or to come from. The third argument is the number of bytes to be transferred. There's like scatter gather I/O, there's zero copy I/O, there's event-based I/O, non-blocking I/O. There's like so many different types of I/O. There's all the socket stuff that you can use to send and receive system calls. There's like a billion different ways of doing I/O. All right, not literally a billion, maybe like a dozen. Each call returns a count to the number of bytes transferred. Each call returns a count. Okay. On reading, the number of bytes returned may be less than the number requested. A return value of 0 bytes implies end of file. Negative 1 indicates error of some sort. For writing, a return value is the number of bytes written. An error has occurred if it isn't equal to the number requested. Any number of Wait a minute. For writing, the return value is the number of bytes written. An error has occurred if it is not equal to the number requested. I don't think that's true, because it is negative returns. But I guess that would be like nothing was written if you get a negative return. Any number of bytes can be read or written in one call. The most common values are 1. Any number of bytes can be read and written in one call. The most common values are 1, which means one character at a time, unbuffered. And the number like 1024 or 4896, that corresponds to a physical block size on a peripheral device. Larger sizes will be more efficient because fewer system calls will be made. Putting these facts together, we can write some program to copy its input to its output. You probably want to use splice for that nowadays. The equivalent of the file copying program written in Chapter 1. This program will copy anything to anything since the input and output can be redirected to any file or device. While read, we write. Pretty straightforward. Using a bit of buffer memory. So obviously this is copying everything from the kernel into user space and back into the kernel. So not ideal. Probably want to use splice or send file. Or I think there's like a man syscall for copy file. Copy file. File. Yeah. File range. Sync file range. Is this? No, this is not the right thing I want. Copy. And if we go to copy file range, there we go. Man to copy file range. So you give it the input file descriptor, the output file descriptor, the size, and you just let it copy. That's a 0 copy. If you look for the word 0, it doesn't say it, but it is. The copy file range system call performs an in-kernel copy between two file descriptors without additional cost of transferring data from the kernel to user space and then back to the kernel. Exactly what we're talking about. And if it's on the same file system, then it will do a copy on write. So it's literally like a 0 cost copy. If it's on a different device, it actually does have to do the copying the bytes. All right. We have collected function prototypes for the system calls in a file called syscalls.h. So we have included it in programs of this chapter. The name is not standard, however. Yeah, because I haven't ran into it before. The parameter, and I think even if we like do like a vim test.c here and do pound include, what is this called? Syscalls.h. That thing doesn't exist. And if do one of these guys here, yeah. Like they have it in the book, it's not there. So they just made this thing up. It's not a standard. The parameter buff size without an E is also defined as syscalls.h. This value is a good size for the local system. If the file size is not a multiple buff size, some read will return a smaller number of bytes to be written to write. The next call to read after that returns 0. It is instructive to see how read and write can be used to construct higher level routines like getCar, putChar, etc. For example, here are versions of getCar that does unbuffered input by reading the standard input one character at a time. Okay, I don't care about that. C must be char because read needs a character pointer, casting C to unsigned char. In the return statement, eliminates any problem of sign extension. The second version of getCar does input in big chunks and hands out the character one at a time. All right, I'm starting to get hungry. I might just hop off here so I can get something to eat before I go to bed. That leads 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13 pages before we get to the allocator. I think I'm going to stop here for the night. So tomorrow, I'm just going to add a little note that we left off here. What was I going to say? Oh yeah, so it's starting tomorrow. I'm going to wake up. I'm going to read those 13 pages. And then we start on the memory allocator reading, which probably isn't a lot. Let's see. They call it a storage allocator. It's 1, 2, 3, 4, 4 pages with some exercise. And I might actually do those exercises if they're related to the memory allocator. And I might just do that in this repo here to get some experience with creating an allocator. And then I do have a project on the project list on my Blackboard behind me that is to implement a bump allocator. So I would like to do that as a separate repo. But yeah, let's go to readme. I'm gonna rm foo here, or let's cat out foo. I think it's just, yeah, that was just for a test thing. Vim readme. I am on chapter 8. Did I mess that up? So it's all chapter 6 stuff. Get diff cached. So I finished chapter 6 and 7. It's a get ignore file, make file. Some test programs that we did today. Cool. Get log 1. It says 5 and 6. Yeah. No, 6 and 7. Sorry, my bad. 6 and 7. So get CI M finish chapter O 6, 7. Get push. Cool. And if you look over here, we've been having a pretty consistent work done each day, so that's good. Good to see. Want to keep that consistency up. This is when I was reading the most of the book, and then I kind of started floundering a little bit here. Yeah. Tomorrow I will pick it back up here, read those 13 pages, then read the section on memory allocation, ideally implement my own memory allocator based on what's in the book. Might even just copy down the text as I read the source code that they give in the book to play with. And then I think we just call it quits at that point. There is the reference at the end of the book. I took the appendice out of the README because I just I thought it won't really be helpful, but maybe it would be. I don't know. The reference manual was intended to be like a standard before the standard. This manual describes the C language specified in a draft submitted to ANSI on so-and-so for approval. So this basically is a standard. The manual is an interpretation of the proposed standard, not the standard itself, although care has been taken to make it a reliable guide to the language. So it might be useful to kind of read through some of it. Some of it I'm just going to like skip over because, I mean, it's a standard document pretty much. But yeah, I might take on the reference manual. I'm not going to the standard library because I don't care about the standard library. And then the last appendice, what was the last appendice? Forget. Oh, there's no index here? Oh no, here it is. Summary of changes. I'm not doing that either. Because there's been a lot of changes since the summary changes. And I don't find that. It's like summary changes between this version and the previous version of K&R C. And the amount of changes between this book and 2026 are so great, it's not even worth even talking about what happened before this book. This is already ancient history. I guess the standard library section, I didn't read the index here. Input, output, character class test, string functions, mathematical function, utility function. All that stuff I don't really care about. But then diagnostics with assert.h, that might be interesting. Okay, I'm going to hop off here, get some food. You'll see me tomorrow morning, and we'll make some progress. Probably finish the book tomorrow morning and implement a memory allocator. Cool. All right, I'll see you tomorrow. Bye.